Hi, everybody. We're supposed to be starting graph theory today, but I did want to take care of one last little item relative to what we were just doing, the counting combinatorics. Um, there was an exercise on the last thing in our online assignment that asked you to figure out things about the cryptographer's alphabet. So I thought it would be nice to show you how that looks if you translate it into code. Um, So I'm just defining an array here, S with the single letter strings in it. Um, if you remember, this is like Python, so it's zero indexed, right? So S sub 0 is the A there, and S sub 1, etc. Um, I'm gonna solve all those problems using code. So let's Let's do the first one. For I in, I hope you know about the range operator. That just returns a list of indices that work in a list of length n. So range 6 gets me the 0 up to 5. What I want to do is nest that loop with another loop that also runs over that same span. Um, let's stop there and see what we can get out of that. I'm letting two variables each independently run from 0 to 5. So the way I can see what's going on in here is to print, let's see, I want the ith element of j and the jth. Did I just say that wrong? I think the ith element of s and the jth element of s. Adding together, because these are characters, it just concatenates them into a string. And there you go. So you see what we're getting out of that. It's all the possible two-letter words. Now, if I wanted to generate them, I've got the right idea here, but what it actually wanted us to do was just count them. So I'm going to set up a counter variable outside the loop, call it starting at 0. And inside the loop, we will increment it. Accidentally hit enter twice. N plus equals 1. And then we could keep track of n, but I think I'm just going to wait till the end of the loops and have it print out what n is. Alright, so we get those two-letter words all the way from AA to FF, and the last thing it prints is 36. That's 6 squared. If we wanted to do this for the problem as it was stated, it was 4, length 4 letters, so we need to have this, sorry, we need a new letter for that IJ. Have a K in range 6. And for L is a dangerous variable to use really in coding, because somebody who's casually looking at your code can easily mistake the L for a 1. But I'm going to be a jerk and use it here anyway. And we got to put those guys inside the loop, or we won't really be getting what we want. And I want to tack on the new letters that the inner loops get us. S sub k and S sub l. And there you see everything from triple or 4 tuples of A's to, oh wow, this is a long list, isn't it? Down to F, 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 and I got 1296. Now, it should be 6 to the 4th power, right? Correct, it is. Let's see how the looping changes if we want to do the next thing, which is to pick a letter and then pick the second letter so that it doesn't match whatever we picked for the first one. All right, I'm going to just copy this so we can paste it down below and collapse the output from our last thing. Paste that in right here. I'm going to want to run do things a little differently though. While I'm inside the first loop, I runs from 0 to 5. It's unrestricted, but j can do anything except have the same value as I. Right? So inside of here, I'm only going to do the remaining loops provided j and I are different. And we could make other changes, but this will guarantee that the only thing that's going to get put out is when I and j are different from each other. I guess I also want to see that k isn't a bad guy, right? But now the conditions on k are tougher. K can't be equal to I, but it also can't be equal to j. Yeah, things just suddenly changed on the screen, I hope, because I realized it was pretty stupid of me to just show you, record myself typing. So we've got this same set of 4 loops, but they're being short-circuited. If we only do something inside the j loop if j is not equal to I, and we only do stuff inside the k loop if k is not equal to either I or j. This sort of breaks us from doing all kinds of looping that would be unnecessary. And in the end, it guarantees that none of these letters are equal to, none of these indices are equal to each other. So when I print this one out, what should we get? Well, ABCD is our smallest one, but then we should see things in all sorts of orders. Let's roll down through this a bit. How about right here in the middle? D, F, B, A. Yeah, neither ascending nor descending, they're all messed around. But have you seen any of them that have a repeated digit, a repeated symbol in them? No. And the number we got there at the end was 360. That's substantially less than what we got in the last time, 4,000 and something. I've already forgot. It was 6 to the 4th power. It was 1296. This is a quarter of that. So what is that number? It's 6 choices for the first guy, 5 choices for the second, 4 for the third, and 3 for the last. Isn't that going to give us 360? Sure. Now what about seeing if we could use some nested loops to generate the things where the symbols are in order? That is, I'm removing the importance of order by just specifying the order. Let's try that. So do I still have this in my buffer? Yes, I do. Okay, so I'm going to change the variables though. I was using these loops using the standard range operator, which is lovely, but it's not going to work for this setup. Yet if I'm trying to make, say, the combinations, that is the unordered arrangements with no repetitions, the smallest I can be is 0 for sure, but the largest it can be is, let's see, the last thing could be 5, the one before that is 4, 3, the biggest it can be is 2. Am I doing all right? 0, 1, 2. The other thing, yeah, that's right. How am I going to change the range for j? Well, I don't want it to be equal to I, right? So I'm going to start at I plus 1. And I'm going to go up to, for this guy, the biggest it can be is 3. Similar change happens to k. K starts at 1 more than the I variable, or excuse me, the j variable. I was trying to delete something that I didn't delete. There we go. So I'm going to start it at j plus 1, and I'm going to move all the way up to 4. And finally, the last variable will start at k plus 1, and the biggest it's going to go to is 5. Some of the loops, these loops are going to have different number of iterations in them at for different values of the variables in the outer loops, right? But, well, let's run this way and see what we get. ABCD, ABCE, ABCF, ABDE. Okay, these are all in ascending order, and that means we've counted the unordered arrangements, and we chose to do this with no repetition. What about that last thing? I would like to get the arrangements to be able to have repeats, and actually we thought our way through that in looking at this guy. Let's just again copy it. Oh, did I tell you what that number was? It was 624. It should have been 15. Was it 15 before I erased it? Yeah, that's a binomial coefficient. By the way, in Sage, there's a function for binomial coefficients. Say binomial. Okay. All right, so what was I doing? Now I want to do the ones where we're allowed to have repetitions. That just means that the loop inside of the I loop is going to start at i's value and go up from there. And it is not true anymore that the smallest I can be and the biggest I can be is 0 to 2. I could go from anywhere from 0 to 5. We will have the possibility. One of the things we're going to count is F, 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 right? Well, yeah. So we do want I to go through the whole range. We want J to start wherever I is, however, and go up from there. So these upper limits are going to be 5s, and the lower limits are going to be the previous loop's variable. Oh, look, there's a syntax error somewhere, it looks like, because these things are highlighted in red. But I don't see it, so maybe it's just the syntax marker is off. Let's see if we got the right sort of things. Here's 4 A's. Here's things like a couple of A's, a C, and an E. These are those ones that would be counted by the commas and blanks idea. And what's the last one? It should be all F's, right? And 126. Now, that was 6 symbols, so 5 commas, and we're taking 4 or selections of size 4, so 4 blanks. That means we're looking for the binomial coefficient 5 plus 4, choose 4, 126. All right, so I just wanted you to see some of the fun you can have playing around with loops and making loops do things other than just the running from one to the end, like so often they do. In particular, I've seen people do something, to solve this problem. If you're supposed to generate all the variables, all the 4-letter words that don't have repeats, just run these same loops, or maybe better yet, the ones that are in order. Run the same loops, but then come down to this stage and have it print. Only do the printing and only incrementing the count if I is less than J and J is less than K and K. So you run through all the loops, and then at the very end, inside the thing where you've already sort of done the work of incrementing everybody, you finally cut out the stuff and only do the real work if your conditions hold. Horribly inefficient programming. So watch out for opportunities to be smarter about the way you nest loops. It's one of the best ways, I think, to optimize code. And unfortunately, that sort of stuff is beyond the ability of an optimizing compiler at this point. Maybe one day, but right now, you have to write the code smarter. The picture here is a floor plan for a building, and tried to draw little dashes around the doorways so you can see them better. And this is actually, an alternative way to think about the problem from Königsberg. Uh, if you have it in this kind of guise, the question is it possible to wander around through this building and walk through each doorway once, and only once? So you're not allowed to backtrack. Once you've gone through a doorway, you kind of say, okay, that's used, and I won't go back through there again. And the answer is no, you can't. But it takes a surprising amount of effort to try to figure out why you can't do it. I mean, you can get pretty far, but you can't ever get all 7 doorways. If you try, usually what happens is you get stuck somewhere. Here I'm stuck over there, and I'll never be able to get to this doorway. And if I had turned the other way, I'd be stuck on this end and have no way out of this room without going through a doorway that I'd already used. And so I'd never be able to get to that one. And so you might think that it's just I didn't start out well or something, but it turns out that it's definitely impossible to do. The point of this version is just to show you another way in which you can have a physical thing that's modeled by a graph. Now, I should at least show you what's the picture that's a graph that corresponds to this arrangement of rooms and doorways. Each room becomes a node. I'm going to draw them kind of big, shade them in. And then each doorway becomes a connection between these vertices or nodes. So I have doors there, there's a doorway that connects those guys, this one, and then 2 more between the middle room and the top room. And you end up getting really the same graph that they got for the Königsberg problem. We're going to launch into a much more rigorous study of graphs. We did have a little intro to them before, but now I want to really get into the meat of this topic. The first section in Chapter 10 is titled Trails, Paths, and Circuits, and essentially my goal for this is for you to understand what those things are. That is, what is the meaning of these words? Because they're words that get used in ordinary language, but we mean something very specific when we talk about them in a graph. Okay, so we talked previously about the history of this problem, how it came about by Euler studying this recreational math question about whether it was possible to take a walking tour of the town of Königsberg and end up crossing every bridge exactly once. The example I did on the whiteboard is exactly the same thing, just restated and made into a game about moving from one room to another of a house and eventually making a path that crosses through all the doorways, but it's got the same graph underlying it. What Euler did was take this picture and turn it into this picture. That everywhere there's a landmass, there became a dot. Everywhere there was a bridge, there came a connection between the dots. Right, so to talk about his proof, you have to know some of that terminology we just talked about. But before we actually talk about that terminology, let's get some even more basic terms now. When you have a graph, G, it is equal to really an ordered pair of things. Well, my brain just had a failure. Let me try that again. G is equal to V, comma, E, where V is a set of vertices and E is a set of edges. So they sound, the letters in there sound like what they should be. V is a set of vertices and E is a set of edges. There's also a relationship between these two sets. There's a what's called the edge endpoint relation. So let's turn this into better grammar. The part about V is a set of vertices and E is a set of edges, that's sort of parenthetical. What I'm trying to do is define what the graph G is. So it's these vertices and these edges together with a edge endpoint relationship. A relation well, let's just say between V and E. And what this relation does, it's kind of you should think of a function. It takes an edge and it tells you what are the endpoints of it. Right? So it's something that looks like this. You take f of some E and you get, well, a couple of the vertices. How about we call them, say, V1 and V2. And V1 and V2 would be called the endpoints of E. I have written V1, V2 as an ordered pair. Sometimes there's an order to these things, and sometimes there is not. It depends on the physical thing we're trying to model. So sometimes there's a directionality in between. The edges go from one thing to another. Other times it's merely the idea of connection, so there is no directionality. So this thing where I've written V1, V2 as an ordered pair, it can also be written as a set. And in fact, it can be written sometimes as a single thing. That's when an edge goes from a vertex, follows some path, and comes right back to itself. V1 and V2 are the endpoints of E. There's one more piece. So look at the terminology we have thrown into here. We've already used some of these, so that's cool. Vertices, those are the dots. Edges, those are the connectors between dots. This edge endpoint thing, so we talked about endpoints. For every edge, you can find a pair of vertices, or sometimes an unordered pair, sometimes a single vertex. But there's a good bit of terminology there. Now, finally, there's a word people use to talk about symmetrically talk about vertices and edges. If you have f of E, if f of E is a pair of things or a set of things, if it contains V, some vertex V, then you say that E and V are adjacent to each other. Pardon me, I just used the wrong term. Adjacency is between two vertices. E is an edge, V is a vertex, and we use the phrase or the term incident in that scenario. V and E are incident. So another piece of terminology. All right, so I think that's going to be enough for us to talk about the definitions of what a path is. Well, before we even get started on paths, we have to do something more basic, which is to talk about walks. So you've got a graph, right? Look at this definition. I've forgotten what page we're on. 679 in our textbook. G is a graph. V and W are vertices in the graph, so there are elements of that big capital V set. A walk from B to W really consists of starting at V and going down an edge and coming to a new V. They're calling it V0, then edge 1, then V1, then edge 2. But you're always alternating between being at a vertex and walking along the path that moves you to the next vertex. So you see this alternation between elements of V and elements of E, the edge set and the vertex set. Right? So we start at V0, well that has to be the original V, and we alternate through these various vertices and edges, and we end at Vn, well that has to be the endpoint, W. Did they say that here? Yeah, they do, right? Right there. I wish I could highlight things. V0 equals V, Vn equals W. Okay, so there's some silly things to get away from. The trivial walk, that's where you start at V and you don't go anywhere. So it trivially matches this definition. It goes from V0 to Vn, but those are both equal to V, and there's no edge in between them. So it really just has that single point. What we have some technical language that we talk about walks that have special characteristics. Okay. So the first one here is when a walk does not contain a repeated edge. Then you call it a trail. Let me try to indicate for you on an actual graph that's sort of a setup. Suppose I have a graph that's just these 4 points and then the edge between them. Now let's call them vertex 1, vertex 2, vertex 3, and vertex 4. And then I'll call this one edge 1, edge 2, edge 3. Heck, let's put another edge across the middle. Edge 4 and edge 5. I could have a walk that went from 1 to 3 that did this. I could go 1 to 2 to 4, back to 1, over to 2 again, and finally end up at 3. Now that would be represented as V1, E1, V2, E4. I went up this way, then I came down here. E4 leads me to V4. Then I went along E5 until I got to V1. And then E1 back to V2, then E2, and finally ended at V3. Nice. Let me just sort of try to trace that again. 1 via edge 1 to vertex 2, then via edge 4 to vertex 4, then edge 5 back to vertex 1, then edge 1 out to vertex 2, then, oh boy, I can't do this left-handed, but you get the idea, right? We went ting, 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 dink. Not a smart way to get there, but it's still a walk. Okay, so walks can be very ambling. You know, you don't have to go directly from where you started to where you wanted to be. Walk, that's an example of a walk. What would we have to change to make it a trail? You can't have any edge seen twice. In this thing, I'm sure I repeated some of those edges. Look, there's edge 1, there's edge 1. So at least one repeat. I guess that's really the only one that I do repeat. But anyway, that makes it not be a trail. So if I wanted to get a trail that went from V1 to V3, I can still be kind of, I don't know, indirect. Would that be a good way to put it? I don't have to necessarily go the fastest way there. I might go V1, be at edge 5 to V4, then go up along edge 4 to V2, and then take edge 2 down to V3. That's fine. What about a path? Actually, this is a path. These have all been paths, so I don't have really an issue with that. But what makes it a walk actually be a path? First of all, it's got to be a trail, so no repeated edges. But to be a path, it also has to not repeat a vertex. Now, did I have an example where we repeated a vertex? I didn't, not in this. Well, this first one was a walk, and neither a path nor a trail, right? Because you see how vertex 1 is repeated, vertex 2 is repeated, edge 1 is repeated. It's hard to imagine how I could make, on this simple of a graph, make it hit a vertex twice without using the same edge twice. It's just a little too small for that to happen, but that can happen in more general, bigger graphs. Like I say, I won't label everything, but let's give it an example that's big enough that you can see that kind of phenomena happening. Suppose here's your V and here's your W. I could make a trail that went from here and back up there, then to here, and then back to there, and then down to W. And that doesn't cross any of the edges more than once, but it does hit the same vertex more than once. So this would be not a path. The trail that I gave up here is also a path, because it doesn't have repeated vertices. Okay. What else do we have in this box? There's a lot of good stuff in here. A closed walk is a walk that starts and ends at the same vertex. Now, for the bits about trails and paths, if you're not going to have repeated vertices, I guess you can't call it a path anymore, because the first one is equal to the last one. That's a repeat. But you could still place this other restriction on it. Maybe you could say, for instance, it's a closed path if that's the only exception. That's actually a very typical way to say it, that you've got a closed path provided it's a path other than that the first and the last vertex are repeats. Now, it is possible to talk about a closed trail, because that's just the edges can't repeat. So you could have the edges not repeat, but the two vertices do. The first and the last vertex do. All right, so closed is a great idea. A lot of graph theory stuff is about wandering around a graph and coming back to where you started. So closed walks are exactly that. A circuit, however, this is one more piece of terminology, that's closed, but it has to, well, yeah, it can't be trivial. So it has to have at least one edge in it. So we don't consider a trivial walk to be a circuit, where you start at a vertex and you go to that vertex without following any edges. Not really what's meant by a circuit. So it has to have at least one edge. In fact, I think it's going to have at least two edges. But no, that's true. That's not true. If you have a loop in the graph, you could start at a node, follow that one edge, and end at that node. Anyway, it's a circuit if it doesn't have a repeated edge. I think the idea is people are thinking about electrical circuits there. And if you imagine electrons flowing from the sink to the source to the sink, the plus side of the battery to the minus side of the battery, they are never going to go along the same branch of the wire twice. They don't take loops around. They start at one spot, find some route through the circuit, and end at the negative terminal. So, yeah, no repeated edges in a circuit. And then simple circuit. Finally, that's our most complicated thing. It's a circuit, so it's a closed walk, but it also, and because it's a circuit, in addition, it doesn't have any repeated edges. But to make it simple, it may not have any repeated vertices. Well, except it's got to begin and end at the same spot, so that one dispensation is allowed to it. There's a great chart here on the next page. Where changed 680. And I think I didn't see this in previous editions of the book, so I really like this, that they kind of lay out the things that are required of things in order to be called a trail or a walk or a path or a circuit or a simple circuit. Right? So the ones that are called walks, the closed walk and the regular walk, you're allowed to have repeated edges. The ones that are called walks are also allowed to have repeated vertices. The trail, you can't have repeated edges, but you can still repeat the vertices. And the path, it's no to both of those questions. You're not allowed to repeat edges, you're not allowed to repeat vertices. Can you start and end at the same point if you're talking about a walk? No, there's no reason why not. There's no restrictions on it if it's a walk, so it could happen. That's why they say allowed. A trail could, but a path could not. Why? Well, a path doesn't have repeated vertices, so how's it going to start and end at the same point? That would be a repeat. None of these have to have an edge in them. They can be trivial. So you can have a trivial path, a trivial trail, or a trivial walk. I don't know if I would just call it a trivial walk. I wouldn't talk about these other things in that scenario, but it wouldn't be wrong to say it that way. A closed walk doesn't even have to have an edge. So you would consider it a closed walk if you just start somewhere and end at that same place and never follow along an edge. Again, it's in a sort of a weak sense, but the point of the ones that are called walks is we're not laying any restrictions on the things, other than for the closed one, the idea that the first node and the last node have to be the same. We're putting the minimal restrictions that you could possibly do. So these latter three, the closed walk, circuit, and simple circuit, they all start and end at the same point. You can have repeated vertices in the first two, but in simple circuits, only the first and the last can be repeated. And for the circuits and the simple circuits, you've got to have at least one edge, because it doesn't make much sense to talk about trivial things being circuits. Okay, so let's get into the general question of Euler. What he was asking about was, is there a closed walk that goes through the edges of the graph for Königsberg and covers all of those edges? Could this be a simple circuit? No. Why not? Think about this. If you have that Königsberg graph, is it possible to go through here and hit only the 4 vertices we see just once and cover all 7 edges? No, because if it's going to alternate between vertices and edges, and you're trying to have 7 edges, you're going to have, well, I guess you're going to have 8 vertices. So there must have been dupes, right? You couldn't possibly do that without. So it can't have, you can't have a walk through this thing that starts somewhere and ends somewhere and ends at that place and covers all the bridges if it also has the restriction that you're only supposed to hit the vertices once. So we're just talking about a circuit. And so the thing that Euler was looking for now, when we look at this in graphs more general than the Königsberg one, is called an Eulerian circuit. There is also the notion of an Eulerian path. And sometimes graphs will have an Eulerian circuit, and other times there'll be graphs that have an Eulerian path. The difference between the two is the circuits are closed, and the paths are not. They start and end in different places. Right. So let me give you an example of that kind of a graph. Here's a graph that's got how many nodes am I adding to this sucker? Looks like 6 nodes altogether, and then I'm sorry, I'm having trouble with the autofocus thing not working. There it goes. 6 nodes and 1, 2, 3, 4, 5, 6, 7, 8 edges. Can I figure out a path through that thing that will cover all the edges once? Can I figure out a circuit? As we saw before, the issue comes with odd things. If you have an odd vertex, one that has, in this case, 3 edges leaving it, that can't be in the middle. That's got to be a start point or an end point. Because if it was in the middle, you would come into it at some point, then you would leave it, and then you would come back into it, and now you're stuck, which doesn't sound like you're in the middle anymore. So that can't be in the middle of the thing. It has to be either the start or the finish. Let's make it the start. Well, that means this other one that's degree 3, that must be your finish. Can you, at that point, actually find a route through this stuff, through these edges that starts at the start and ends at the finish and goes through all the other edges? Probably. It's not that hard, actually. Let's see, go down this one, then up there. Let's come back here, then out here. I'm allowed to hit these vertices more than once. I hit the finish, but I'm not done, so I have to keep going. Then take care of that edge, and then that edge, and I finished. Got to the thing. So, I just showed you an Euler path, or I prefer the phrase Eulerian. A lot of people just say Euler without turning it into an adjective. Yeah, so that's an Euler path, or Eulerian path. What about an Eulerian circuit? Well, if you're to have a circuit starting and ending at the same point, you might as well say it never starts or ends. It just you keep going. So you could kind of think of it as starting and ending at one vertex, or maybe you go somewhere else along the circuit and think of it as starting and ending there. Yeah. So what's the problem for odd vertices there? You can't have any. There's a theorem. I started to write out the theorem by hand, but I remembered that I had made the scan of the pages of the book, so we can find the theorem written here. First, it defines what an Euler circuit is. Dr. Epps says Euler, where I would say Eulerian. And then she has this theorem. If a graph has an Euler circuit, then every vertex of the graph has positive even degree. Positive means that nobody has degree 0. What would that mean to have degree 0? Well, that would be what's known as an isolated vertex, one which you would never be able to arrive at. So it would be impossible to have a circuit of the entire graph if you can't arrive at some of the vertices. But the fact that it's even is this problem I pointed out about odd degree of things just can't exist in the middle of such a walk. They serve to trap you. So there's a nice description of it, but here's the contrapositive. If you have a vertex that has an odd degree, then you surely do not have an Euler circuit. Now, they haven't talked about the converse of the statement there, and that's an interesting question. Suppose you do have a graph that has all vertices of degree that are even. Is it possible to find an Euler circuit? And the answer is almost always. But there are exceptions. For instance, one important thing is the graph would need to be connected. You have to be able to get from one component of the thing to the other so that you can cross. You'd only be able to cross the edges in the part that you were stuck in. If there was another piece that was separated from you, you'd never be able to get to those guys. So you need to have a connected thing with all even degrees. And I believe that's all that's necessary. All right, so last thing, not to be outdone by the Swiss, there was an Irish mathematician 150 years later who proposed a problem rather like Euler's, but he chose to look at the nodes rather than the edges. So this Königsberg thing was about crossing all the bridges. The guy I'm talking about was named Rowan William Hamilton. Very interesting personality, I think, but this isn't a history course, so I'm not going to get into that. Hamilton proposed this problem as a entry in a thing called the mathematical triptos, which was a test for people graduating from Cambridge. I may have that wrong, because he taught at Trinity College, so maybe it was at Trinity. In any case, here's the problem. He, I don't have an actual, just a model of one of these things, so I have this kind of, well, it's a Rubik's Cube, except it's not a cube. It's a shape called a dodecahedron. So I just wanted you to be able to visualize what shape Hamilton was talking about. It's, the vertices are actually the corners of this thing, and the edges are the literal edges, the one-dimensional paths from between any of the corners of it. So that, he asked, was it possible to wander around the edges of this solid shape and manage to hit all the vertices once, but never repeat an edge? So he didn't want us to have any repeats on the edges. That doesn't mean you have to hit every edge. The thing you had to hit was every vertex. And it seems like a difficult problem, but it turns out to be mostly just a problem about visualizing, because people can't hold a three-dimensional object like this in their minds very well. So if you draw the graph in the flat, then you'll be able to solve this problem. So it's actually not a hard problem, but the general question of, are there circuits, technically these get to be called cycles, where you don't have repeated nodes, and except for the first and the last, and you don't have repeated edges, simple circuits, maybe that's the way I should refer to them, and you cover every vertex once. Does that exist in a typical graph? No. Okay, I'm gonna try to draw the edge graph of the dodecahedron here for you. It's a little bit tough. What you need to do is sort of imagine grabbing it by the bottom pentagon. This shape is all pentagons, right? Every face of it is a pentagon. Grab it by that bottom pentagon and pull. Expand out the bottom pentagon into a great, huge, big pentagon. And the rest of the graph will get stretched somewhat, but not that much. Every corner is degree 3 in that graph. Let me show it to you again. You see how there's 3 edges coming towards a single corner on this? That's the degree. So there's sort of stubs that come in from here, from each of these dots that are on the outer pentagon. And also, by the way, these are supposed to be 5 cycles, aren't they? Look at the red thing on the top of this. It's got 5 vertices and they're all connected in a little cycle around it. Every face is like that. So I'm going to draw these so that we kind of get that feel. There's going to be, it's very distorted, so don't be upset about that, but there's going to be 3 nodes in a line for each of these edges of the outer pentagon. Okay. Almost there. Everybody has to have degree 3. Remember that? And these guys that I created here, they're the 5th dot in the pentagons there, but they don't have degree 3 yet, so they'll have a little nub sticking off of them. And then these have to be pentagons too, so, well, what has to happen? They must all be joined. And we sort of come back to the middle. We've got the pentagon that forms the top of this thing. So if you know anything about the dodecahedron, its name is Greek for 2 and 10. 2 and 10 faces. It's got 12 faces. And you can count them up. There's 5, 6, 7, 8, 9, 10, 11. And this big outside one is the 12th one. It's kind of not easy to visualize that, but the outer region on the plane serves to to sort of represent the 12th face of the dodecahedron. All right, can we trace our way around that graph and hit every node once? Sure. Yeah, I mean, I would make yourself a copy of that and go to town. Try it out. You just have to strategize a little bit. You want to make sure that you leave yourself an escape route to come back to where you started. But I think I won't actually do that for you because it's a good challenge to try it. The tough thing is to figure out what that graph looks like, rather than have to, I don't know, what you could do is build paper models of this thing and try to trace on it with markers or something. Nah, you'd make one mistake and you'd be ruined. But by being able to draw the thing into flat and not really affecting the problem, you get a graph theoretic thing. These are called Hamilton cycles, and they're an important category of thing because, well, for a couple of reasons. One is that there's many ways to think of this, but one particularly nice application of graph theory is multiprocessor machines, the architecture for supercomputers. So in such an architecture, you want to have a bunch of CPUs that can talk to one another. The dots would represent CPUs, and the lines between them would be high-speed communication lines, buses, right? And if you put too many bus lines in there, you spend too much effort, sending communication packets around. So all you really want is sort of a minimal set of connections, so that if this processor needs to talk to this processor, you can get a message passed over there. There's a lot of different message passing schemes, but one of the big ones is called a token ring, and it requires you to be able to sort of assemble a circuit, a cycle, in fact, that goes between all the processors. So finding one of these Hamilton things would be ideal. If you wanted to have a dodecahedral CPU layout, you could do that. Now, what actually happens more often, if you're actually talking about supercomputers, is they use high-dimensional hypercubes as the connectivity, and then there's a neat problem trying to find Hamilton circuits in a large dimensional hypercube. You might have 1,024 processors all trying to intercommunicate and keep a concurrency going while they work on a problem together. All right, so we will finish out Hamilton circuits for different sections, different times, but later. And but that's going to be it for today. Our activity coming up, I'm going to have you actually do some practice at finding both Hamilton circuits and Euler circuits. And so you'll need to know the conditions where you stop and say, wait, you can't build one for the Euler circuits. For the Hamilton circuits, I won't mess with you too much yet. They'll all be doable, but it's a good challenge to be able to find them, even when you know that they exist. Sometimes it's hard to find a particular one. All right, see you soon.